Okay, so I've converted in-class notes from today, Thursday, October 16th, into an iChem lesson, either for those of you who weren't here or just if you needed a little refresher, just because I'm not going to be here for the next couple of days, and I want everyone to be prepared to be successful in your assignments while I'm gone. So take out a periodic table and a calculator, your notes from today, the viewing guide, and follow along. Some of this you'll already have in your notes. You can fast forward until the part that you don't have or to the part that you need review on. It is totally up to you. This is for you and for you to be successful. So first of all, we talked about the fact that a mole is just a base unit. We can define it in three ways. With the mole triangle, we'll look over in a minute. It represents a specific number. In the same way, a dozen represents 12, and a pair represents 2. A mole represents 6.02 times 10 to the 23rd. Now, this is a very, very large number. After that decimal point, there are 23 more places in the number. This is a large number because atoms are very, very, very small. So the mole is useful so that we don't have to count. We're not counting individual atoms. We're counting them in terms of moles most of the time. So 1 mole equals 6.02 times 10 to the 23rd. We call this Avogadro's number. So when we talk about using conversion factors and the appropriate conversion factor being Avogadro's number, this is the number we are talking about. The other number we're talking about as a conversion factor is molar mass. Molar mass is much like our mass of a single BB in our exercise earlier today. It allows you to relate one of something to counting large amounts of something. The molar mass has units of grams per mole. For an element, remember, if you're looking on the periodic table, you'll find the molar mass. So just a couple of things real quick. Have the periodic table in front of you. Follow along. If I'm talking about the molar mass of magnesium, find magnesium over in the second column, group 2. It's 24.305. Calcium right below it, 40.078. Strontium right below it, 87.62. These molar masses are standard and specific for every single element. The mass of a compound is a little bit more confusing, but really not by much. We calculate it and we use a process much the same way we added up our electrons for Lewis dot structures. If you need a review on this, actually I'm not going to put it all into this video because it's a lot of tedious typing, but there's just so many great tutorials out there on the internet. Literally just Google finding molar mass, and the first thing that comes up shows you exactly what I did in class today. So just Google finding molar mass. First thing that comes up shows you exactly what I did. Walk through a couple times for finding the molar mass way. Okay, defining the mole. We talked about this mole triangle. It can be defined in number of particles, atoms, molecules, formula units. That's down here on the left in the triangle. Can be defined by weighing a sample. That gives you the mass. That's down here on the bottom. When we're talking about gases, it doesn't make a whole lot of sense to find the mass on a balance, so we talk about gases, we talk about volume. All of those can be related back to the mole by our conversion factors. So if we're talking about the conversion between particles and moles, our conversion factor is Avogadro's number. That's 6.02 times 10 to the 23rd. If we're talking about conversion factor from mass to mole, that conversion factor is the atomic mass. Is the molar mass. For elements, it's the atomic mass that you find on the periodic table. For compounds, we just talked about a minute ago, the process of how to find the molar mass of a compound. If you want to Google, there's plenty of tutorials out there on the internet if you were confused in class today. If you have volume, the conversion factor is molar volume, which is this 22.4 liters. Now I want you to notice looks a little bit different than the road map we made in class today. I'm highlighting just the conversion factors. The math operations are as follows. As you go towards the mole in any place in this diagram, doesn't matter where you start, your math process will be divide by the conversion factor. As you go away from the mole in this diagram, doesn't matter where you're going, the math operation is always to multiply. Just depends on which conversion factor you're going to use. Okay? Always look for where you're going, where you're starting, and where you're going. So these are examples. Some of you, we got to these in class today. Some of you, we didn't. We'll go through them here. Either you're seeing it for the first time or you're seeing it for review. Either way will help. Okay, so first, I have aluminum is often used for structures such as high-quality bicycle frames. Compute the number of moles in a 10-gram sample of aluminum. Again, important questions. Where am I starting? Where am I going? I'm starting. What I have is mass. I have 10 grams, so I'm starting here in the mass. What I want, I'm asked to compute the number of moles, so I'm going to moles. From mass to moles. My roadmap tells me if I'm going from mass to moles, I'm dividing by the molar mass. So create my dimensional analysis. I start with 10 grams. Remember, if I'm going from mass to moles, I'm dividing by my molar mass. The molar mass of aluminum, I need to look at my periodic table. I find aluminum, I find the molar mass of 26.98 grams, and that's the mass of 1 mole. So the grams cancel, I'm left with 0.376 moles of aluminum, and that's my answer. I looked at where I'm starting, where I'm going, and I followed my roadmap. Next example. If a scientist uses 0.5 moles of magnesium, how many atoms of magnesium did she use? Okay, so where am I starting? My given is moles. Where am I going? I'm looking for atoms. Atoms is one of my options when I'm talking about particles. So I'm going from mole to particles. My conversion factor here is Avogadro's number. So I start with a half a mole, 0.5 moles. When I'm going from moles to particles, my roadmap tells me to multiply by the conversion factor, 6.02 times 10 to the 23rd. And that's atoms per mole. The moles are in opposite corners, they cancel out. I'm left with atoms, specifically 3.01 times 10 to the 23 atoms of magnesium. During cellular respiration, a cell releases 0.25 moles of gas. A container of what volume is needed to hold this gas? Again, same questions every time. Where am I starting? Where am I going? Well, I'm given moles, so that's where I start. What am I asked? I want volume, so that's where I'm going. If I follow my roadmap, I go from moles to volume. My conversion factor is my molar volume, which is 22.4 liters per mole. And my roadmap tells me that I need to multiply. So here we go. Set up my dimensional analysis. I start with my given, which is 0.25 moles of oxygen. And I multiply by my conversion factor, 22.4 liters in 1 mole. I multiply across the top. I end up with 5.6 liters of oxygen. Everything we've done so far has been one step. You can go from any of these quantities here within the triangle. In this example, it says calculate the number of formula units in 45-gram sample of iron oxide. specifically iron 2 oxide. We can sort of think of formula units as another way of saying molecules. So if I have 45 grams, where I'm starting is mass. Where I want to go is formula units, another word for molecules. That puts me way down here in particles. There is no direct link from mass to particles. I have to go through moles. So I'm going from mass to moles, and then I'm going from moles to particles. So I set up my dimensional analysis, starting with 45 grams. To go from mass to moles, my roadmap tells me I need to divide by my molar mass. But first I need to figure out what my molar mass is. I have iron oxide. I have 1 iron and 1 oxygen. This should totally be a 1. Cross out that 2 and make it a 1. 1 iron and 1 oxygen. Then go to my periodic table, I see that iron's molar mass is 55.85 and my oxygen's molar mass is 16. I just add 55.85 and 16 together, keeping that 2 there covered so you don't get confused, and I end up with 71.85 grams per mole. So remember, my roadmap told me when I'm going from mass to moles that I'm going to divide by my molar mass. 71.85 grams per moles. As I was talking just that minute, I realized I keep referring to the roadmap. You should have that in front of you. We made it in class today. It's the one with the arrows and the math operations with your conversion factors. It's the one on your viewing guide. Have this out with you when you're doing all of these calculations. It will greatly help you. When I'm talking about roadmap, that's what I mean. Okay, so now I have my masses have canceled out. I'm left with moles. I'm here. I want to get to here. When I have moles and I want particles, my roadmap tells me to multiply by Avogadro's number, 6.02 times 10 to the 23. In this case, we're talking about units, formula units per mole. Now I've canceled my grams, I've canceled my moles, I'm left with my formula units. 3.83 times 10 to the 23rd units of iron oxide. I multiplied across the top and then divided from the bottom. Okay, so here are a few examples from class on Thursday. In that packet, that POGL packet I gave you today, if you follow through and you read the, do question in order, it sort of walks you through all of the logical thinking behind doing all of this math. These notes are a little bit ahead of where we ended up in class today on the POGL. So when you're going through the POGL, some of it will seem like review, but still go through the motions of it because it'll kind of feed itself into helping you learn some other concepts based on this. So good luck, and I will see you guys all on Tuesday.